Team, this is a review on RC circuits. So in this equation is saying like, hey, the switch is left at position B at a very long time. Position B, right here. And notice that it's not connected to a battery. Because it's not connected to a battery, but the circuit is closed, what's happening right now is that our voltage across the capacitor is decreasing over time and it's reaching zero. So this is what is happening at switch B. Okay. Until it reaches complete zero, that's why it's saying that. So once it switches to A, our capacitor is completely discharged. But after it switches to A, over time, right here, switch A, I'm going to write it down right here, switch A. Over time, our capacitor starts charging until it reaches maximum voltage. And that maximum voltage is actually equivalent to the battery connected to the capacitor. So now that we got that out of the way, the first thing is step one. It is converting our PRC equation, which is charge equals to capacitance times the EMF battery times 1 minus e to the negative t time over tau. And tau is the resistance times capacitance. So step one is convert. If you want to jump, hey, by all means, but just in case, using this equation where voltage equals Q over C, which is charge over capacitance. So if I divide this equation by C, I in turn change the equation to reflect voltage instead of charge. So voltage over time is equal to EMF times 1 minus e to the negative t over RC. The next thing, step two, is use the Kirchhoff's rules to solve for current, because it is asking us to calculate the magnitude of the current over a specific time. And in this situation, we use Kirchhoff. We could derive, because in deriving, if I write here, current over time is equal to the derivative of charge over time, then we could definitely do that if you want to derive. But I usually use this method because I am trying to avoid you deriving, because I know how much you hate it. But if we go and do a loop around the circuit, then we are considering V, which is the EMF, and V is also equivalent to EMF, just to let you know, okay? Minus the voltage across the resistor, because we are following current, right? So if current goes from high to low, like we were talking about in the other video, then it is minus. And then capacitor also goes from high to low. So capacitor is also, the voltage across the capacitor is also negative. And this all equals to 0. So now we just replace voltage, where the EMF is still in place. This is equal to current over time times resistance minus the equation here that we have, the voltage across the capacitor, EMF, 1 minus e to the negative t over RC. EMF, again, going back to this equation, is V. So if we multiply, let's just put this V minus or plus VE to the negative T over RC. Notice that I just replaced the EMF with V because it's the same thing. And then I multiplied EMF times 1 and then EMF times negative E to the negative T over RC. And I get this. Notice that there's a negative here, so this becomes positive. So these two, V, cancel out. And I am left with I of T equals V over R times E to the negative T over RC. And that is your answer.